In this video, we're going to cover section 1.17.1, homogeneous catalysis. A homogeneous catalyst is a catalyst that exists in the same phase as the species involved in the reaction. So if a solution phase reaction involves an enzyme that's soluble in solution, then we refer to that as a homogeneous catalyst. So enzymes, acid-base, catalyzed reactions, these are typically examples of this type. The catalytic depletion of stratospheric ozone by atomic chlorine is a well-known example of gas phase catalysis. Now, ozone will naturally undergo degradation in the presence of atomic oxygen to give you molecular oxygen, but this reaction is accelerated in the presence of atomic chlorine. So let's look at that example in more detail. So in the mid-1970s, Sherwood Rowland and Mario Molina proposed that chlorine atoms catalyze the decomposition of stratospheric ozone by the following mechanism. The catalytic efficiency of chlorine can be determined using standard techniques in kinetics. The experimentally determined rate law expression for the uncatalyzed reaction is shown, where the rate of the uncatalyzed reaction is first order in the concentration of atomic oxygen as well as ozone. Now, the stratospheric temperature where this reaction occurs is roughly 220 Kelvin. At this temperature, the uncatalyzed rate constant is equal to 3.3 times 10 to the 5 molar minus 1 seconds minus 1. However, for the chlorine catalyzed decomposition of ozone, the rate constants at 220 Kelvin are as follows. K1 was found to be 1.56 times 10 to the 10 molar minus 1 seconds minus 1, and K2, same order of magnitude, 2.44 times 10 to the 10 molar minus 1 seconds minus 1. Now, to use these rate constants in determining the overall rate of reaction, we first need to develop a rate law expression for the catalytic mechanism. So the rate law expression for the catalyzed reaction is shown. We're interested in the decomposition of ozone. It's found in the first step of that mechanism. It's dependent upon the rate constant K1, the concentration of ozone, as well as the concentration of chlorine. Now, in this mechanism, both chlorine and the chlorine monoxide are intermediates. So if we apply the steady state approximation, the concentration of intermediates is taken to be a constant, such that we can use the symbol X to represent a sum of those intermediates. So the sum of the intermediate concentrations is equal to the sum of the chlorine atom concentration and the concentration of chlorine monoxide. Now, the steady state approximation can also be applied in evaluating the differential rate expression for the concentration of chlorine. And as shown, these are the two steps. So 2 terms, chlorine is involved in both of those steps. And after applying the steady state approximation, we can equate the net rate of change of the chlorine concentration to 0. In doing so, we can equate these 2 terms to 0 and then rearrange for the chlorine monoxide concentration. Now, if we take this expression and we substitute it into this expression for the sum of the intermediate concentrations, we can solve for the concentration of the chlorine atom as shown. This is the intermediate species that's found in our initial rate expression for the decomposition or depletion of ozone. So now we can take this solution, substitute it into our expression for the decomposition of ozone, and we're left with our final expression for the catalytic reaction. So we have our rate law expression for the catalytic mechanism. In the stratosphere, the ozone concentration is much greater than the atomic oxygen concentration. So under those conditions, the rate law expression for the catalyzed reaction becomes simply K2 times the concentration of the sum of the intermediates and the concentration of atomic oxygen. So again, We can come to that conclusion because if this term is much greater than this term, then we're going to get cancellation of additional terms, and we're left with the product of just those three variables. Now, if we take a ratio of the catalyzed reaction versus the uncatalyzed reaction, we can cancel further. There's a further reduction where the concentration of atomic oxygen cancels out in both expressions, and we're left with the following quotient, where we have K2 times the concentration of the sum of the intermediates over K uncatalyzed times the concentration of the ozone concentration. What we also know is that in the stratosphere, the concentration of ozone is roughly 1,000 times greater than the sum of the concentrations of the intermediates. So we can include that into our ratio, which then reduces it down to just a quotient of the two rate constants, K2 and K uncat, and we'll include this factor of 1,000 in our comparison. So if we take those values that we presented in the first slide of 2.44 times 10 to the 10 molar minus 1 seconds minus 1 for K2, and we compare that or divide that by the rate constant for the uncatalyzed reaction, even taking into account this factor of 1,000, we have a 74-fold greater depletion of ozone in the presence of these intermediates than without. And so a significant increase in the rate of ozone decomposition when these chlorine atoms are present in the atmosphere. So you may be asking yourself, where does stratospheric chlorine come from? Well, Rowland and Molina proposed that a major source of chlorine was from the photolysis of chlorofluorocarbons, commonly known as CFCs, such as CFCl3 and CF2Cl2. These were common refrigerants used at that time. These molecules are extremely robust and persistent in our environment, but when released into the atmosphere, they readily survive transport through the troposphere and into the stratosphere. Once in the stratosphere, these molecules can absorb a photon of light with sufficient energy to dissociate the carbon-chlorine bond, producing chlorine atoms. This research led to the signing of the Montreal Protocol in 1987, where 197 parties agreed to phase out the industrial use of CFCs. Today, CFCs have been replaced with hydrofluorocarbons, which don't undergo the same dissociation to provide those chlorine atoms. However, as of January 2019, the Kigali Amendment to the Montreal Protocol came into effect, which now promises to reduce the use of HFCs by more than 80% over the next 30 years, because they are considered greenhouse gases with a high global warming potential compared with those original CFCs. So even today, we're still looking for substitutes for CFCs and now HFCs that are less harmful to our overall environment. So this is one example of homogeneous catalysis. In the next video, we'll look at enzymatic catalysis, another example of homogeneous catalysis. But if you have any questions about this example, by all means, send me an email. Thank you.